Yeah, or the identity at least in the matrix system, yeah.
So, but, I mean, I guess if I knew, well, anyway. I mean, that's helpful, but that's just one bit of, I need three things like that. Of course, we can find the inverse.
Oh, we're looking for the inverse.
Yeah, that's what we have to do if we're going to find the.
Would be the cofactor expansion divided by like the determinant, right? All those divided by the determinant.
No, we could do that. It seems hard. The usual.
We have some zeros. No, if we expand by the first column, you get a 0.
Yeah, but you know the usual. You know the usual method. You guys remember that?
Probably, but
Been a while.
yeah.
All right, so I'll do it. 0, 1. We've got minus half, minus 1/2, 0 root 3 over 2, minus root 3 over 2, right? And then 1, 1, 1. All right. You concatenate with the identity over here. Right?
Yeah.
And then you do row operations until you move the identity over to here.
Okay.
So like,
We
first,
did not do this method.
oh, interesting. So row 3 minus row 1. And I'm going to go ahead and multiply row 1 by 2 just because I hate fractions.
Okay.
So I've got 2 minus 1 minus 1, 2, 0, 0. I'm going to multiply the second row by 2 also to get rid of the fractions. Hopefully I won't mess. You got to be careful when you do more than one thing at once, but I'm going to try to save myself some writing. Alright, so going back here. This minus that gives me 0. This minus that gives me 3 halves. And 3 halves again. Okay, so row 3 minus 1. So we swept out, swept out the first one. And then I think the next thing I'm going to do is I'm going to multiply this last equation by 2. And I'm going to be lazy and just do it RACI style. So 2. Put some minus 2 here and a 2 here. Then you see something nice happens if I add row 3 to row 1. So that's being my next kind of.
Oh yeah.
That's nice. So I get 2. Oh, but not just that. I should add 3 times row 1 to row 3, because then the 3 that cancels, you know. So 3 times row 1 is 6. 0, 0. I still got the 0 root 3 minus root 3, and what did I say? 3 times row 1 plus row 3, so that's 6 minus 2, which is 4, 0, 2, 0, 2. Now, we'll find out soon if I'm right or wrong, right? Because we can check, at the end we'll check with matrix multiplication, so hopefully I won't make a mistake, but if I do, it's like, we'll find out. Now,
Multiply by root 3 that one by, no.
yeah, I
multiply
like
by
that, I like that. So that's root 3 minus 3.
And you get the 2 root 3.
2 through here. And then if I subtract
Yep.
row 3 minus row 2,
And then just pull stuff out. Oh, wait.
I
Divide
got
by 2. No.
divide that by 2.
Yeah.
So that's going to be 3.
And add it.
6, 0, 0, 0, 3, 0.
0, 3. That's the second note.
I had to add, you said add row 2 plus row 3, right?
Yeah, and then that last row stays the same, and this one turns to.
When I add that to that, I get just root 3, right?
Yeah. And then you gotta divide some nasty stuff. So.
Right, so then we divide by 6, we divide by 3, we divide by 3. So that gives us the identity, right?
Yeah, 2, yeah. 1, 0, 0, 0, 1, 0, and then 2 over 3 is 4, 6,
Okay,
0,
2/3.
2, 3.
1/3, right? And then
No, you divide in, no, it'd be 2/3. No.
2/6, yeah.
Yeah, it was, yeah. 3 over 3.
Okay, yeah.
Root 3, yeah. 1 over 3, and then, yeah, same thing. Alright. Let me,
So,
I'm gonna check this real quick. 2, 3, 0, 1/3, negative 1/3, root 3, oh, they got root 3 over 2.
where?
This term, they got a root 3 over 2. Maybe I put it in wrong. Oh wait, no, that's fine. 1 over 3, yeah, root 3 over 3, 1/3. And there's that 1/3 on the bottom, negative root over 3, and then, well, yeah, you got it.
Okay, so now of course we can check it, right? Like
Yeah.
I said, f inverse of 1, 1. Now 1, 1, keep in mind, is in our 3 notation would be 1, 0, 1, right?
Yeah.
And that's supposed to map to 1, which in the other R3 notation is 1, 0, 0 in H3. So if we do 1, if we try multiplying this by 1, 0, 1, notice what we get. We get 2/3 plus 1/3, which is 1,
Mm-hmm.
0,
Yeah.
0.
Yeah, checks.
So anyway, after some suffering, f inverse, what was it? F inverse of x plus iy, comma t, right? You notice there's a third.
Yeah.
Just pull a third out, 1/3. And I'll write that matrix again. 2, 0, 1. Minus 1. Square root of 3, 1. Third party. You're not supposed to do third party right now. I don't know what that means, but yeah. No third party. That's your 3 again. But just to track back to the other notation, that would be 1/3 of 2x plus t, right? That's the part that goes with the number 1,
Mm-hmm.
plus j times minus x plus square root of 3 times y plus t plus j squared minus x minus root 3 times y plus t. There's a third that multiplies the whole thing. So I think you can see this is like, you know, not something I just write down off the top of my head. Like,
Yes.
I gotta have to work a little bit to find the what's interesting here though is it's so easy to write the map down in the forward direction because of the generator thing.
Yeah.
What's also interesting though is now we can figure out what is that element of the three hyperbolic numbers that effectively is like a copy of the complex numbers. Like what is the element? So in C cross R, right? You have I comma 1, which I comma 1 squared is I squared 1 squared, right? Oh,
Negative 1, 1.
curses. Yeah, that's negative 1, 1. Huh. That's not what I wanted. So that's not really I, is it?
No.
I mean, it's...
Negative
Oh.
0.
Yeah, that's the... Oh, Yeah, I squared is minus 1, 0, right? Ooh. Oof. Oof.
Does that cause a problem?
Only in my intuition. I just wonder. There's certain problems I haven't solved yet, and I feel like this might have a bearing on those. But my point was, we can now find out what I comma 0 looks like, quote unquote. Like what is the I comma 0, or what's the I comma 1 in H3, right?
Oh, we inverted it.
But anyway, I mean, like I don't know what this means, but F inverse of I0, I mean, what is that? That's A equals to 0. Oh, I guess in my current language, X equal to 0, Y
But V would have to equal 1.
Y equal to 1, T equal to 0, right? Nothing here. Y is 1, right? So square root of 3 over 3. And what happens here? Minus j squared times square root of 3 over 3, right? Can I erase this?
Yeah. This is all on my whiteboard in James's room. Calls himself Evan when he comes to school in Alabama.
Uh-huh.
And so I was like, oh, you're James's roommates? And he's like, who's James? I was like, forgot. Didn't want to make a new identity.
Some people just change their name when they come to school just for the sake of...
They don't want to be who they were in high school, I guess.
Huh, interesting. So if I call this thing alpha, right, and I study alpha squared, what do I get? So I got like square root of 3 over 3. I'm going to leave that up front, right?
Mm-hmm. J minus j squared. Let's go ahead and do that. Write that out. That'd be 3 over 9.
Mm-hmm.
And then we get, so that's 1/3, and then j squared, so you get j squared, first term, you get my j to the 4th 2, and then you get 2j, well yeah, but it's like 2j third.
Right, 2j cubed,
Yeah.
and then like you said, plus j to the 4th.
So j squared we know, j to the 4th we know, is it j cubed?
So we got, because j cubed is 1, right?
Yeah.
So this is, and this j to the 4th is,
J.
is j.
So j is equal to omega. So we could do the omega squared minus.
So we got, yeah, minus 2, well, j is j though.
Yeah.
J is not equal to omega.
Oh, okay.
But, we got minus 2 plus j, plus j squared, yeah.
Yeah. Okay.
Now that's supposed to be, that should be, this should be equal to, right? F inverse of what?
I0.
So I0 squared, right?
Yeah.
Is minus, so this should be F inverse of minus 1, 0, right? Minus 1, 0 is x equal to minus 1, y equal to 0, t equal to 0 in our language formula. There's a third, right? See here, so x equal to minus 1. So the 2x plus t just gives us,
I'm sorry, wait.
so I'm trying to do like f inverse of minus 1, 0 now to see if it matches.
Yeah. So that'd be minus
2,
0,
yeah, 2 plus 0 plus j times,
just that term, which would be 1, just j. 0, 0.
oh, minus 1 is b1, just plus, thank you, plus j, very good, yeah. I was thinking it's minus 1 for a second, but I forgot there was a minus.
And then same thing, plus j squared.
Plus j squared. Which of course,
Same thing, yeah.
what was wrong with my thinking, Audric, is like I was thinking that there is a copy of I, that there's a copy of I in C cross R. And the question is, what do I mean by that? You know, I say that, right? There exists a copy of I in H3, right? What does that mean? What do I mean by that statement? Like, I thought that that statement had meaning. But the question is, what do I mean by that? What kind of, see, like,
Well, yeah, because in the complex I is like a distinct point.
yeah, I usually think of that in the sense of like I is the square root of minus 1 kind of idea. So what I really mean by that is I squared equals to minus 1, right? You know, is there an element whose square is minus 1, right? But there's another question, right? I can replace that. See, here's the thing that is naively wrong with my thinking, is like I assume that there's a copy of I in C cross R.
Yeah.
But is there an element of C cross R such that the square of that element is minus the identity? Is there?
I gotta think for a second. I think it's actually a possibility. No, it's fine. I gotta look back at what we were doing before.
So, like, you know, I mean, we can use, I'm going to erase the things that I can erase.
You can erase everything if you want.
Yeah, I think I can, I might want this formula here. I'm going to save that. I'll just save that. We don't need the matrix arithmetic anymore.
In C cross R, you need.
So let's bring to bear the things we've worked out on this problem. Let me state the problem unambiguously, okay?
Yeah.
So I'm asking the question. I'm going to ask the question in. I'll ask the question in H3. You know, if we look at the equation, sometimes I can write it, sometimes I can't. Z squared equal to -1, can we solve it, right?
Yeah. Okay, so square root on both sides.
But I don't know what the square root is in H3. Man. Now, however, I can trade that question.
To 1 C cross R.
Yeah, so let's feed it to F, right?
Yeah.
Is it F? F go that way?
Yeah, we're calling it F. They were calling it F inverse, so.
I mean, F goes from H3.
Into C cross R.
Okay, so let's let F of zeta equal to W for the sake of,
Yeah.
and W is itself x plus iy comma t, right?
Yeah.
So can we solve W squared equal to, F of -1? F of -1
Minus F 1.
is minus, very good. Perfect. Sorry, I was about to get this out, but you're absolutely right. Which is minus 1, 1. And so what this really is can we solve the equation x plus iy squared comma t squared, right?
Yeah.
Equal to -1 minus 1.
T squared gets you a non-real number.
That's right. We cannot do this because it's not possible to solve t squared equal to -1 where t is a variable.
Yeah.
So there does not exist a
Nah.
I in H3, or, for that matter, in C cross R.
No.
Despite the fact that if you're sloppy like me and you're thinking to start with, you go, oh, I've got complex numbers, comma, real numbers. I got I's in there. Well, yes, I do on the surface of things, but in the spirit of having something that squares to minus the identity of the algebra, I do not.
No, you have to have C cross C. Then you would. C cross C, you definitely could get an eye out of that.
Ah, yeah. Good point.
But,
Hey, good point. Yeah, C cross C has II.
yeah. Don't get you to know your old one.
Stupid Popeye. But they had the 4-hour marathon of Popeye in the IMDb. People used to eat canned spinach.
Like I was
Do people still eat canned spinach?
No, I don't think so.
I mean, because the thing about Popeye is it's all based on the predicate that
He gets super strains.
But he gets super strains from eating healthy
Yeah.
canned vegetables. It's messed up. Like, who wants to eat canned? I mean,
I used to like canned fruit when I was a kid.
that is true. Like, that can be good.
Those peaches, those oranges.
Oh yeah. But you're right. This is I squared, which is -1, which is minus the identity. So in C cross C, we do have a.
I don't know what C cross C is going to be equivalent to in isomorphism though.
Well, C cross C is a 4-dimensional algebra,
Okay.
and I mean, you could ask the question: is C cross C isomorphic to?
H4?
Yeah, you can ask that question. And one of the strategies for deciding whether or not algebras are isomorphic is if you find an element of a particular pedigree, if you will, in one algebra, then it has to have that same structure in the other.
Yeah.
And this is also true for groups, right? I don't know if you guys started looking at this question in group theory, but one way to judge whether two groups are not isomorphic is if you can find an element of order 4 in your group A, group G, and then your other group H doesn't have an element of order 4, they're not isomorphic because an isomorphism of groups maintains the order of elements. And that goes on here too. I mean, you can look at the group of units of any of these algebras. And the structure of that group of units has to be preserved by these isomorphisms.
What would J3 equal? JQ then?
See, there's another kind of algebra we look at. Just also a couple of my notation. But I think I used C3 for it.
Mm-hmm.
I'm not 100% sure about the notation here, so I gotta look at my papers and junk, but C3 would be the algebra generated by K, such that K cubed is minus 1. You know?
Yeah.
So it's things of the form A plus BK plus CK squared. K cubed. So, I mean, if you're going to ask two algebras are isomorphic, you should find two at least at the same vector space dimension, yeah?
Yeah.
This is also three-dimensional. So, question, is this isomorphic to H3?
No. K cubed is equal to negative 1. If you would map it back inversely through F,
What would F be though?
like, my thinking is that in J cubed in H3 is 1.
Yeah, J cubed is 1. But, well, that's a question, right?
Yeah.
What if you, instead of having square equal to minus 1, what if you just play a slightly different game? What if instead of playing the square game, you played the cube game?
In H3?
In H3. Can you find a solution to zeta cubed equal to minus 1?
It's a hyperbolic space, though. How are you going to get a negative 1 out of that?
I don't know, but can we? So if that's minus 1, then...
Yeah. Pull that out.
Uh-huh. See, now your problem, your beef with t squared equal to minus 1 is gone.
Yeah.
T cubed equal to minus 1. Well, we have real solutions
Yeah.
to that, just one of them, but
Yeah.
minus 1, right?
Yeah.
T equal to minus 1.
No, but I cubed. I cubed equal to negative 1, that doesn't work.
Well,
Yeah, it has to equal 1. You wouldn't get a negative 1, 1. Or negative 1, negative 1.
well, the question is, all right, so this pair of equations, right,
Hmm.
give me two things to solve, right? The one is, let me rewrite this as z cubed.
Hmm.
The complex number z cubed equal to minus 1, right?
Yep.
And real variable cubed equal to minus 1. Now this one we can solve.
Yeah.
It's the cube root. The cube root of any real number.
Can you do the prime factor thingy?
Yeah, this just gives us 1.
No, I know that. I'm talking about here.
Ah, this one, yeah, so z is what? Z is an element of the third roots of minus 1, right?
Yeah. Wouldn't that 1? Negative 1?
Minus 1 is e to the pi I, right?
Yeah.
So e to the pi I, what is the
Also,
first?
2 would be negative 1, wouldn't it?
Oh, yes, thank you. So e to the pi I, so like, I'm trying to solve this
Yeah.
cube equal to, so I can use the thing we talked about earlier. Principal third root of e to the pi I, e to the pi I over 3. Right?
Yep.
And then so like z is equal to e to the pi I over 3, or it could be e to the pi I over 3 times e to the 2 pi I over 3, or e to the pi I over 3 times e to the 4 pi I over 3. Those are your three solutions for,
Yeah.
those are the three different solutions that give you minus 1,
Mm-hmm.
and you cube them.
In the complex space. Okay.
So not only is there a solution to this, there are in fact three distinct solutions.
Yeah. Which tells us what though?
It tells us that there's hope that H3 is isomorphic to this.
Yeah.
And in fact, it suggests that there's more than one isomorphism. Because we could either send K to, you know, this comma that, or this comma that, or that comma that in C cross R, and then, so, I mean,
C cross C.
yeah, so like, sorry, to explain my logic more fully, I'm saying C3, then track back to C cross R, and then track back to H3, right?
Yeah.
So that was with F inverse, right?
Wait.
And this is the G mapping, which I haven't even written down yet, but
Yeah.
like G of
So we already know C3 and C cross R are isomorphic to each other.
we're trying to understand if that's true or not. I actually think that the easier way, I mean, so I've been attacking this problem in this way because I think it was fun to play with the things we've already done today.
Mm-hmm.
But what I usually do is just point out this. If I have, alright, so I'm trying to look for something whose cube is -1. If I know that J cubed is 1, then minus J cubed is
-1.
-1. So to go directly from here to here, I would suggest the map like, let's say, phi of k equals to minus j.
Yeah. Do that. But can you prove that if two things are isomorphic to each other, that the last, like,
If you can map a generator to a generator,
yeah.
and the entire algebra is generated by that. I mean, if it's an algebra that is generated by one generator, all right, and you can map generator of one algebra to the generator of the other algebra, then they're isomorphic, yeah. And it does have to, it's not just that, like, it's not enough to just map generator to generator. You have to map the generator to the generator such that the characteristic equation, the equation which characterizes the target space, is satisfied by the image of the generator of the original space.
Okay.
So what I'm saying here is like that satisfies that criteria, because the thing is that psi of k, which is in H3, right? I need that cubed is 1.
Yeah. It's 1? A -1?
Oh, curses, that's still what I need. It's the wrong way to say it. Yeah, this is supposed to be -1. Yeah, -1. Yeah, I'm sorry, Roderick, I'm not saying this quite right yet. You're right that that's -1.
Yeah, I'm still confused on what C3 is.
Oh,
Is C3 what you define here?
C3 is yet another algebra.
Yeah.
That an example I'm introducing. It is three-dimensional algebra generated by k, such that k cubed is -1. We can look at the like regular representation of it. And it looks like this. And then because we're working in R3 where 1 is E1, k is E2, k squared is E3, going back to like day 1 or 2 stuff. The next one I multiply by k, so I get, a goes down here, and c times k gives me k cubed, which is -1, which puts a minus c up here, and then b moves down here. And then next up, you get minus b, minus c, a, I believe.
I'm not gonna lie, Benjamin's crying, shifting my focus. Okay, let me come back.
It's understandable. Eventually, when you have enough children, you grow cold and heartless to their cries.
Gotta get there first. This, you know, there's like marriage before that. Like, yeah, you skip a whole bunch of steps here.
That's good.
First, I need a job. You know.
You know, like people talk about advantages of like 3 children over 2 or whatever. Like the advantage of like past 3 is like eventually you grow less sensitive to their needs, and so it makes it easier.
That's what my old coach told me in high school.
Really?
Just like your first baby, like you're like, oh, I'm gonna break this thing, and then like you start throwing it around. Like, that's alright.
That's fine.
Okay, so getting that, and then to find the inverse, is this to find your inverse mapping back into H3, that matrix?
This one?
Yeah.
Oh, this is just the regular. This is
Regular
a,
representation. Okay.
this is a element of the regular representation of what I call
C3.
C3.
Yeah. Okay. Alright. We have a lot of questions here. I have a week to kind of work through these. I definitely think C3 and H3, it feels isomorphic. I think it will end up being, depending on what you choose here.
Well, you can just, like I said, you can just use the map.
Psi.
Yeah, I mean, if we do phi of like a plus b k plus ck squared is a plus bj plus cj squared.
Mm-hmm.
But I'm supposed to send k to minus j, right?
Yeah.
So there.
Yeah.
That would be an isomorphism. It does send 1 to 1, right? So like side 1 equal to 1.
Yep.
And phi of k, of course, is
Make 1.
minus j.
But yeah, minus J, that's right.
So you can see that phi of, so like this is the thing, phi of k cubed minus 1 is phi of k cubed minus phi of 1, you know?
So we got phi of 1, and we have phi of k.
Mm-hmm.
So we get 1. We get 0. No,
Oh, and I'm an idiot too.
Yeah, we get.
K cubed plus 1 is 0, right?
Yeah.
My bad. Sorry, I think too hyperbolically sometimes, but
KQ plus 1 is 0, yeah.
so of course this is
0.
minus, yeah, it is 0 minus j cubed plus. That's the kind of that's why I glibly said, oh, if you said generator to generator, that's enough. No, that's not enough, because like you could define a map. Let's say, I don't know. I need another letter. I use this thing. I haven't used this thing yet. There, this guy. I'm mapping from, let's say, complex numbers to the null numbers.
Yeah.
And I could make 3 lines of I equal to epsilon. Extend linearly.
That won't work out.
No.
Yeah, I squared is not equal to
I mean,
0.
and I mean, let's say psi of 1 is 1 as well.
Yeah.
So, this is psi of a plus bi is equal to a plus b epsilon. It's a lovely map, but it's definitely not an isomorphism because
So I squared is
yeah, psi of I squared plus 1
that should be 0,
should be 0.
but it's not going to.
Exactly, because that is
0 plus 1.
and but the thing is, I can't just, I gotta be careful what I mean by this, right? I mean, is this equal to question mark psi of I squared plus 1,
Yeah.
And this over here is, of course,
E.
epsilon squared
Which is
plus
0.
1, which is 1.
I mean, if it's a true isomorphism, yes, but it's not.
Right. So sending,
That fails if it's a true isomorphism.
yeah, so sending generator to generator, and even sending 1 to 1, do both those things, that's not enough. it also has to preserve the equation which defines the generator being what it is.
Yeah.
So for H3 and C3, we're great.
Yeah.
So, all right, so I think maybe you're, so I think at this point I've kind of shared with you some of the main examples. Ideas like direct product algebra, looking for isomorphisms between things, right?
Yeah.
So, what do you think H4 is?
H4?
Oh, do you want some coffee?
No. Like what's it isomorphic to?
Yeah, I mean it's okay. So let me tell you, there's a theorem.
Okay.
The theorem says that any semi-simple algebra is a direct product of matrix algebras of fields. Now, matrix algebra. We'll talk about some other time. All right, but. In the case that it's commutative, that theorem just drops down to a semi-simple commutative algebra is actually a direct product of the real and the complex numbers as many times. So that's at play here. This is a semi-simple commutative algebra because it, well, the careful definition of that, you have to explain what semi-simple means, and that's like a little bit of a story, but in short, this is, and that's why this happens, in part. And, of course, this is also a semi-simple commutative algebra, so it is also a direct product. Now, it didn't have to be this, right?
No.
There's another three-dimensional commutative algebra, which is R cross R cross R.
Yeah. Yeah.
That would be something else. That's a different algebra that's not isomorphic to this. Because, like, R cross R is not isomorphic to C.
Yeah.
In C, you have the I, which is squares minus 1. In R cross R, you don't have that.
No.
So as we think about four-dimensional algebras that are commutative and semi-simple, there are really only a couple of cases that you can think about. So like if A is a four-dimensional, which I'll just write it this way. If you think about A being R4 with some product and it's semi-simple and it's commutative, then there's a theorem which says it has to be a direct product of fields.
Yeah.
In particular, it either has to be, well, it could be R cross R cross R cross R
Yeah.
cross R, right? It could be R cross C.
Oh, yeah, because that's 4.
Or it could be
C cross
C
R.
cross. Well, how about just C cross C? Now,
And then, yeah.
and that's kind of it. Now, we also have other isomorphisms. Like we can look at this different ways, though. See, this is isomorphic to H2 cross H2.
Oh.
Because H2 is isomorphic to R cross R, as we've explored. So this is also isomorphic to two hyperbolics across the complexes.
So you're trying to, so H4, I feel like H4 definitely has to be isomorphic to H2 cross H2. Because your J in H4, your J fourth, so you get, no, it'd be J cubed, so you get 1, 2, what would J cubed need to be? Because J cubed isn't going to be equal to 1, right?
Yeah,
and J4.
right. Of course it's a different J, right?
Yeah.
So we have 1J, J squared, J cubed, and
J4 is equal to 1.
J to the fourth equal to 1. Right.
And then for that, you could have J squared, J squared. Because you can map it to the 1, 1. Because 1 is 1.
Oh, I guess we could look and see, is there a, can you find, well, definitely H cross H has a, well, lots of things have things, I'm sorry, I only tell you half, I only use half my words, and assume you can hear the rest of my thoughts, it's wrong. I'm thinking, can you solve element squared equal to 1? Yeah, I can do that in the reals. I can do that. I mean, that's not. I mean, lots of things have that, right? Yeah.
J3 J4 definitely maps. I mean, no J1, 2, J squared, J. That's good.
See, like this one, you know, the regular representation of this looks like. So if I say alpha equal to A plus BJ plus CJ squared plus DJ cubed, right?
Mm-hmm.
Then the matrix representation of alpha using this is E1, E2, E3, E4. In R4, it's going to be alpha J squared, alpha J cubed, right? It's a 4x4 matrix, and it has the form A, B, C, D, and then the D gets pushed. The A gets pushed down. Then the C gets pushed. And then so that's what the regular representation looks like. And of course we could study the determinant of that being 0. That was part of what helped us get convinced that H3 was C cross R.
Yeah.
Oh, so we should try to map.
You're trying to H2 to C then?
So your intuition was H2 cross H2. Your claim. Let's go with your claim, which is based on a hunch, which is H4 is isomorphic to H2 cross H2, right?
Mm-hmm. I'm still thinking of a J3 though. But H2 cross C could work in the way you're thinking with the matrix thing. But J3 would have to be.
I honestly don't remember right offhand, but let's stick with this. Let's try that.
Okay.
So my challenge to you at the moment, as I'm about to make my coffee,
Okay.
is can you tell me what should J be over here? And instead of let's help ourselves out a little bit, and okay, what should J be in this space? So like, let me write this typical element here. Something like, you know, A1 plus B. I'm going to call it J1, comma, A2 plus A1, B2, J2. Just to have some nomenclature which separates the concept of J1, J2, and J down here.
Mm-hmm.
Of course, J1 squared is 1, and J2 squared is 1. All right, and here, A1, A2, B1, B2, these are all real constants. So my question is, what should J be here such that, you know, quote unquote J to the 4th power is equal to 1, and yet this is really, I'm really regretting this quote unquote notation. we call it J bar. It's really not much better. J bar squared, J bar Q, you know, are distinct, right? Because you need that, right? You need that 1J, J squared, J cubed are distinct, but you want J to the fourth to be 1. So,
I have a couple of hunches on what J could be, like from H4's J.
it's got to be something of this form, right? Like J bar has to be something. I mean, according to our you got to pick something in here, yeah. And the 1 is really 1, 1 here, right?
Yeah.
So what can we choose for A1, B1, A2? I mean, in our previous scheme, we made J, let's call it squiggle, equal to
You're talking about C cross R?
the C cross R. We made it E.
Pi.
It was kind of complicated, right?
Yeah.
1? Yeah.
Yeah.
And if you think back to the H2 isomorphism, we made J map to 1 minus 1. But let me get rid of this stuff here. It's just distracting. Where's my mug? Hello. What are you doing?
One J.
1 share. Now, square of that.
One square. It's one.
Well, first of all, you mean 1J2, right?
Yeah.
But the square of that would be 1, 1, which is 1. So it goes to 1 too soon.
That's okay. We needed to do it in the fourth.
Yeah, what if we did J1, what if we did J1, J2? Oh, but J1, J2 is the same problem, right?
Yeah.
And I was thinking J1 minus J2, same problem. Oh, do you know something that has order 4 in the complex numbers?
No. One sec. No, I get a J. Can I do difference of squares? So there'll be 1 minus J, 1 plus J.
I'm gonna eat some of this cake. Otherwise it's going to be wasted.
Equals 0.
Oh, actually, no. I'm not eating some cake.
No, I don't work either.
Yeah, I think maybe, I'm just now thinking maybe C cross H is the way to go.
It does, but I don't think the plan is completely wrong, because there's something you can factor. Like, I just have like a hunch that there's something you can factor, and where like, by the time you get to the J4th, that the fourth tuple will be 1. I just gotta like try
But
some.
think about I, right?
Uh-huh.
What's I squared?
That's 1, -1.
Right. What's I cubed?
It's I cube. -1, -1. So that'd be -1, -I.
Mm-hmm.
And then it'd be 1. So that would work.
So like, what if we could use like I? No,
No, I'm fine.
I comma. Now this is so I'm giving up on the claim. I'm going to your other claim, which was H cross C, right?
Yeah.
How about J cross I? I mean J comma I.
J comma G squared would be 1, -1, and then J cubed would give you the 1, 1, or J quad give you the 1. But there's something here. Wait, please. Well, what is it? What gives me J to the 4th? Or give me 1 once. Some if it equals some A plus BJ, and then this is be 1. You can even this could be plus or minus 1 actually. So do that. Wait. Yeah. Square root J. Square root J1.
But I don't know what square root of J is. You mean like J as in hyperbolic J?
Yeah.
Mm.
Because you square that, get J, fourth it, 1, 1, 1. Because you don't have to have it in H4. And, well, wouldn't that just turn backwards on you though? Because it would have to, if J squared is equal to 1, right? If you took the square root of that.
So if you could find a square root, you're saying if you could find a square root of J,
Yeah.
then that to the
It would
fourth
map.
power would be 1, 1.
Yeah, but
Huh.
yeah,
And yet, that would not be a generator. And yet, that's not a generator of H cross H.
no.
But I guess,
What are you thinking? IJ or JI?
I guess it depends whether we're doing H cross C or C cross H.
Yeah. What did we do for? We did C cross R.
I mean, it's just a question of, who sits in the front seat of the, well, that's actually more of a question, like who gets to ride shotgun, that's a serious question, especially if you're a certain age, but, yeah, if we do C cross H, then it better be I comma J.
Yeah, that better. That would work.
See, because then
Yeah.
square it, you get -1,
Yeah.
1. If you cube it, you get -ij, and then if you do the fourth power, you get 1, 1. So I believe that's the one.
Yeah, that's the more upbling.
H4 is C cross H. So that's kind of neat.
Does it generate though?
H2 is isomorphic to R cross R. H3 is isomorphic to R cross C. And H4 is isomorphic to R cross C or H cross C.